Anyway, so as the next and final in our series of talks related in many ways to bootstrap percolation, I'm very pleased to welcome Paul Smith from the University of Cambridge. And please, Paul, thank you for coming and take it away.
Is that okay? Is it on?
Unless you speak, we can't.
Okay, I see. Okay. So yes, thank you very much for the introduction, and thank you very much for the invitation. It's a great pleasure to be here at a very diverse conference, and I hope that so many of you probably, well, until this morning, had never heard of bootstrap percolation. I would just actually, this is not the last talk related to bootstrap percolation. There's another one on Wednesday. Fabio Martinelli is going to talk about... oh, today, okay. You've got a whole week of this stuff. So for those of you who don't know much about this, then hopefully this will serve as a bit of an introduction. So, oh yes, a pointer. Okay, so some of these people are in the room. The first two are in the room, Paul Ballister and Bela Bolovash, just next to each other here, the front. So this is really just here in case you don't know who some of these people are. This talk is based on a series of papers which are all joint with different sets of people, and this is an exhaustive list. So the important thing is that Paul is Memphis and Cambridge, and Bela is Cambridge and Memphis. There was some sort of logic, there was some method in the madness there, I think. So, okay. So what is bootstrap percolation? Well, if you're a physicist, it's a monotone version of the Glauber dynamic, zero-temperature Glauber dynamics of the Ising model. And I'm afraid that's about as much physics as there's going to be in the talk. Although I will mention Glauber dynamics again at the very end. If you're a mathematician, especially if you're a combinatorialist, it's a monotone two-state discrete time Tilly automaton on the integer lattice. So until relatively recently, all bootstrap percolation, it always meant our neighbor bootstrap percolation. And this is the following module. So well, I've written it on z to the d or zn to the d. This is the discrete torus, but it applies equally well on any graph. So you have some sites which are initially infected or occupied, whatever you want to say, and this set increases in a monotone way. And new sites become infected if at least r of their 2D nearest, well yes, if you're in z to the d, 2D nearest neighbors are already infected. So the setting in which we're most interested is where the initial configuration is random. So you have a density p of infected sites to start with, and you would like to know what the probability is that this grows to infect the whole graph, either z to the d or zn to the d. And so this critical probability measures when that's likely to take place. Well, I said greater than or equal to a half. So lambda just stands for one of these two graphs. If you're in the this makes more sense in the finite graph actually. In the infinite graph, this probability is always either 0 or 1. I will just briefly mention that this is this is right at the interface really between probability and combinatorics. The probability in this question comes at time 0, what the initial configuration looks like. Of course, thereafter everything is entirely deterministic. So the study of what happens after time 0 is entirely combinatorial. And we know a lot about this critical probability. Hopefully this is an exhaustive list of people who've worked on this question ever since Van Enter, who proved the first rigorous result on bootstrap percolation in 1987. And he proved that with the two-neighbor model on z squared, the critical probability is 0. So any positive density will percolate. It was Eisenman and Lebovitz who first realized that actually looking at what happens on a finite graph is much more interesting, and all of these people continued their work and culminating in this sharp threshold theorem, which was quite recent. So this theorem effectively ended the study of our neighbour bootstrap percolation. So Yoshi Balak was also here, Baylor, Ugo Jimno-Kapan and Rob Morris. Basically they closed off this area of study by this really lovely theorem. So this is classical bootstrap percolation. And the start of the story here is we wondered whether, well, it seemed likely that the properties enjoyed by the our neighbour model should be shared by a much broader class of monotone cellular automata on Z, initially on Z squared and then later in Z to the D. So this is the definition here of the most general possible monotone cellular automaton, so homogeneous and local, sort of assume it's included in the definition of a cellular automaton. But if it's monotone, then this is as general as it could be. So you have some sets, x1 up to xm, and you just ask, so if you want a site to become infected, you just ask, is the appropriate translate of one of these sets already completely infected? And if it is, then your site becomes infected. Right. I'll come to examples in just a moment. So yes. Yes. So you have a collection of subsets of Z to Z minus the origin. And you just ask, so if you want a site X to become infected, you ask, is there some xi, some set xi, such that the translate of xi by x is entirely infected already? So this includes all of the our neighbour models, because you can just take the xi to be...
Lots of examples?
There'll be examples in just a moment, yes, sorry. Yeah, the examples are coming up. There's all sorts of examples coming up in just a moment. It's all in completely the wrong order, I apologise. But I want to tell you the definition, and then I'll tell you all the examples. And not just tell you examples, I'll show you the examples in action as well. So we'll see some examples happening. So I just want to tell you what the stable set is. The stable set... so in Z squared, so can I write here? So you take a direction u in the circle, and you take the entire half plane, the discrete half plane here, and you ask what happens under the action of this process. And it's always the case that either everything becomes infected or nothing becomes infected. It's exactly one of those two always. It's very easy to show that. And so it's called, the direction is called stable if nothing happens, and unstable otherwise. Okay, so let's see what that means. So examples. So two neighbour model. Yeah, so in general, our neighbour module, the update rules is they're just all of the 2D choose R subsets of size R of the 2D nearest neighbours of the origin. So all subsets of this of size 2. So all 6 pairs here, if you have any 2 of these 4 blue crosses, then you get the site in the middle. That's what that picture's supposed to show, very badly. And the stable set is just the 4 main compass points, north, south, east, west. Because if you have a half plane in one of these directions, like the north one, and you ask what happens under the action of this process, the answer is nothing. But if you take any diagonal half plane, which of course really looks like this, then everything goes. So you start with all of these, and so on, everything goes. Okay. So another one's something called the Duarte model, which looks very similar. You're just missing this site here. So you say this becomes infected if at least 2 of these 3 are infected. And now the stable set looks quite different. It's got this entirely complete closed semicircle on the left-hand side, which really represents the fact that this model only goes rightwards and sort of slightly asymptotically upwards and downwards, but it definitely doesn't go leftwards. It's very hard for you to have stuff on the right of a site you want to become infected and become infected. You can't. Okay. And one last one I want to mention, DTBP. So this stands for directed triangular bootstrap percolation. And again, it looks very similar to Duarte. It's just two of these three blue crosses, but this cross is now moved to here. It's called DTB because if you draw it on a triangular lattice rather than on a square lattice, it's much more elegant. And the stable set looks like this bizarre thing here. Okay, so hopefully now, by the power of magic, yes. So now we can see some of these. So we start with the two-neighbor model. And this is the classical two-neighbor model. So this is these are all on 300 by 300 tori. And this is 10% initial density. So with 10%, it sort of all goes all at once and all grows, and eventually everything disappears. So it's all going to go, and that's what happens. Okay. So at 5%, we go down to 5%. You can see there's there's more local effects where sort of almost everything stops. We just get a small number of regions that have just grown large enough, and then they go, then they're off, and they eat everything. So that's now dead as well. So this is much closer to the critical probability. Oops. Okay. So Duarte, remember, was the one I said grows to the right. Or I could see 4%. So it appears to. There's some more down here. It has stopped. It has stopped. Okay. So nothing happened there. So Duarte, remember, is the one I said that it grows rightwards. So you need 2 of 3 of north, south, and west to become infected. This is what it looks like. So maybe again, it starts quite dense. And it's not very clear what's going on. But you can just about see it going to the right. And you can see these big regions forming, and they'll eat everything. And what about a little bit less dense? So again, now you can see most of it has sort of stopped in this kind of metastable state, but there's a couple of regions where it's just gone now. So much closer to the critical probability.
What sense is there a critical probability here?
So the probability, there's this density p where the probability of percolation is a half. So I didn't see where that would come from. I mean, we don't know what that is. I mean, yeah, we only understand these asymptotically, but we don't. So, yeah.
On the whole plane, it's probability. Oh, I see. It's not like the initial model where it doesn't matter what the probability is. Here
Oh, on the whole plane, it's the same here. It actually is 0.
So what does it mean for a critical? What does it mean to be critical?
Because this is not a plane. This is a torus. This is finite. It's completely different.
N by N.
Yeah, n by
Depends on
n.
your initial condition.
So it's just a function of n, of the size of the
a
grid.
function of your initial data, right? Your initial randomness.
But it's random. Yeah. So we're asking
So
what the density p needs to be, so that the probability of percolation on an n by n torus is a half.
Function of N.
It's a
function of n.
Yeah.
Yeah.
That's what I meant.
Oh, and so finally, GTBP. Maybe I'll start with a small density. This sort of grows into these kind of slightly triangular shaped regions. Maybe at 12% we can see some bigger ones. And if our luck's in, we might get so 13%. Sometimes this goes, sometimes it doesn't. Probability for you. It looks like this one's going to go, so. I think it's just about going to go, yeah. Okay, it's too late. It's too late. It's gone. Okay, so hopefully, so this is what some of these things look like anyway. So they have a lot of properties in common, but as we'll see in a moment, there's a lot of things that are very different about them. Right. Okay, back. Excellent. So, what can we? So what? Right. So the lovely the simulation's very lovely. What's actually happening? So we define this very, very general model, and in 2 dimensions, turns out that there's essentially 3 very different types of behavior that these models exhibit. And so you can partition all of these models into one of 3 classes. And which class it's in depends only on the stable directions I mentioned, which is quite an extraordinary fact, actually. So the rough, large-scale behavior of these models depends only on which of these directions are stable and which are not. And so here's the classification. It's super critical if you can find an open semicircle that has no stable directions. So supercritical is these are the easiest ones to grow. So something that looks, where a stable set looks like this, typically it will just grow rightwards. It will grow very, very easily. So in some sense, these are the least interesting of all, although I'll come back to that point later. Subcritical if every semicircle contains infinitely many, which is equivalent to an interval. So this, you may recall, was the last example, GTBP, the one that grew with the weird, not quite triangle things. And it's critical otherwise. And critical includes 2-neighbor bootstrap percolation, the traditional model. Okay, so these are the 3 classes. And why are they correct? Well, if you're supercritical, then your critical probability is polynomial. This follows from the deterministic lemma, because that supercritical, the definition I gave was quite weird, something to do with semicircles, but it's actually equivalent to there exists a finite set that goes forever, has infinite closure. So there exists, so on the infinite on z squared, you can take a finite set of sites, and when you run the process, you get an infinite number. So that's true if and only if it's supercritical. If it's critical, then critical probability is logarithmic. And then finally, a bit later, we prove that if it's subcritical, then you have a non-trivial critical probability on z squared, in fact. So it's important, these are finite things. So on z squared, they're both 0, and not so interesting. Finite things, but here on z squared, it's strictly positive. And actually, I say it's strictly greater than 0, it's strictly less than 1 as well in all interesting cases, including DTBP. So when bootstrap percolation was first introduced in 1979 by Chalupa, Leith and Reich or something, their hope was that it would exhibit behavior like this, and it was a great disappointment, actually, when Van Enter proved that it didn't. So this result shows that there are actually very similar models that do exhibit this sort of behavior. There's lots to do here. The bound we have here for DTBP is about 10 to the minus 150 or something. And less than 0.3 or something. Okay, so this is the sense in which there is a correct definition. So the rest of the talk is entirely about critical models. These are the ones that behave in 2 dimensions, a bit like 2-neighbor bootstrap percolation. So we just said that we can prove that the critical probability is logarithmic. But what can we say more specific than that? This is just a constant in the exponent. So what was known, so the order of magnitude, i.e. the critical probability up to a constant factor, has been determined previously in a handful of cases. So we mentioned this one lots of times. The duality one was proved by Mountford in 1995. So some class of models called symmetric balanced star threshold models. So these are things where, in order to get a new site, you have something like this that's symmetric, centrally symmetric, and you need a certain minimum number of these, and some other conditions hold as well. And in some sense, one of the most interesting ones, this anisotropic module. So this doesn't fall in the above category, in this category, because it doesn't meet this technical condition that it's balanced. It's not balanced. I did this one as well. So at least 3 out of these 6. Okay, so this is, I believe, an exhaustive list, up to very minor modifications of what was known. And they're all examples of threshold models and all exhibit some kind of symmetry. So before I tell you the next result, I have to tell you some definitions, so I apologize. Right. So the result's going to be about what that exponent is, what that critical exponent is, and it depends a lot on, it depends completely on, you take a direction u, and my tick skills are such that u is going to be north. And you want to understand the difficulty of growing in direction u. And the difficulty of growing in direction u is governed by these quantities alpha plus of u and alpha minus of u. So alpha minus of u, for example, says what's the minimum number of sites, which might well be outside of this gold half plane here, so that if you add those sites to your initial configuration, which is just the half plane, you get an infinite number of new sites to the left of the origin. So suppose you have some bizarre model where these 4 gold crosses give you an infinite number of sites to the left, like this. Then you say alpha minus is 4, provided there's no configuration of size 3 that achieves the same result. Again, alpha plus is defined similarly on the other side, and then the alpha of u, difficulty of going direction u, is just the minimum, is the easiest of those 2, provided you can grow in both directions, or both are finite. It could be infinite. It could be there's no finite set that achieves that. Okay, so this is the difficulty of growing in direction u. So what's the minimum, roughly speaking, what's the minimum number of sites you need outside to get infinitely many new ones, roughly speaking. And then difficulty of the entire circle is just min-max. It's just the hardest direction inside the easiest open semicircle. Okay. Right. And finally, this was where balanced before. I have to mention what balanced means. It says there's a closed semicircle where you can do just as well as in your best open semicircle, which sounds subtle, but it's extremely important. So, for example, maybe we're going to this board. So with 2 neighbour, the stable set is these 4 points, and they all have difficulty 1. Because in each of these 4 directions, if you have a half plane, you just need 1 new site and you get an entire new line. But with duality, for example, it looked like this. This here. And this was 1, but these are infinite. Because remember, it was both directions had to be finite for it to be finite, and it turns out if you're at the end point of an interval, then you're infinite. So it's not so duality is not balanced, but 2 neighbour is. That's what I've just said. Okay, and then so that's the theorem. So the critical probability up to a constant factor for every single critical model. It's either balanced, in which case just 1 over log n to the power of 1 over this difficulty alpha of the entire circle. Or it's unbalanced, then you get this log n squared correction. Okay. Can we do better than this? what about sharp thresholds? So we know some of these. You may recognize this list. So as of a couple of months ago, this list is exactly the same as what was previously known up to a constant factor. So we know sharp thresholds for all of the models I've mentioned. But again, that's an exhaustive list, completely exhaustive list. And there's no sort of, we don't really have any ideas for how to develop a more general theory at the moment. There's a huge open problem in 2 dimensions to develop a general theory. So, of course, sharp thresholds exist just by Frege-Cali, but the question is, what is the location? So what is the constant? Is there a constant? So that's all 2 dimensions. What about going up into high dimensions? So, so again, the limits of my drawing skills in 3 dimensions. So in 3 dimensions, what do stable sets look like? Well, just in 3 dimensions, we already have 2 nice examples which exhibit completely different behavior. 2-neighbor and 3-neighbor. So in 3 dimensions, 2-neighbor bootstrap percolation has just these 6 stable directions: north, south, east, west, and in, out. And any direction that's remotely diagonal will just go. It just goes. But with 3-neighbor, you get every point on the unit sphere that has at least 1 0 coordinate. So these 3 circles here. Okay. There's a couple of examples. And what's the significance of those? Now, so when you, so this picture here is supposed to be here, very close around here. So just looking at this point here on the sphere, there's some direction, and looking locally what the stable set looks like, and it looks like that. And so just drawn a circle very close to the point where it crosses, and looked at the intersection of that circle with the stable set. And of course you notice that it looks like it's just the 4 usual compass points on the circle, which is just what the stable set looked like for 2-neighbor in 2 dimensions. And lo and behold, that's not a surprise. So let me just rub this out. So, say in 3 dimensions we have some cube already, and we're running 3-neighbor bootstrap percolation. We have some cube, and we ask what happens, how does growth take place on the surface, on this face of this cube? And the answer is, it's exactly 2-neighbor bootstrap percolation, because every site here already has 1 neighbor inside. So it's got 1 neighbor inside, so it's just reduced to needing 2. So if you already have this, you just run 2-neighbor on the surface. And so I've said what induced processes, but this is just saying that in order to understand these high-dimensional things, we just try and understand what happens in slices on the surface of our object that's growing. Okay. And it turns out that in a particular direction, what happens on the surface, it looks a lot like the intersection, this intersection of a stable set with a circle near to the point that you care about. So yes, it's not a coincidence. So the 3 types of stable direction in 3 dimensions. So the supercritical ones. So for example, with the 2-neighbor model, you just have single points. That's supercritical. And the reason is because if on the surface of the sphere you just have a single point in a small circle around it, intersection of that with a stable set empty. Uninteresting. It's also true if you have a straight line through the point. It's not empty, but still supercritical. Those correspond to critical directions in 2 dimensions. So with 3-neighbor, remember that some of the points on the sphere, there were these 6 points that look like this, and then around here, we say this is too hard because around here, the stable set looks like it looks critical in 2 dimensions. And then there's nasty ones that are subcritical. So, right, and actually, this is all you really need to know to understand the rough behavior of these models in 3 dimensions. And similarly, in actually all dimensions. So this applies in high dimensions as well. Okay, so now the supercritical and subcritical, as before, and they're basically the same. Supercritical is you've got an open hemisphere is empty, and subcritical is every hemisphere has positive spherical measure. And then there's 2 types of critical. One that says it's a bit like 2 neighbor, and one that says it's a bit like 3 neighbor. Okay, so these are the 2 types. And it's a bit like 2 neighbor if in the easiest hemisphere it only contains directions that are at most 1 hard. So they look supercritical, like the 2 neighbor model did. And it's 3 critical if the easiest hemisphere only contains 1 or 2 hard directions. Okay. So just recall this theorem again. The only reason is because I just want to emphasize this 1 over log, this is r minus 1 times iterated log of n. Not because I'm going to say we have anything as good as that, but just emphasize the 1 over log r minus 1 of n. So what we do have is that proof's definition is correct in that if you're r critical, you do get the 1 over r minus 1 times iterated log of n up to a constant in the exponent. Okay, so this is the new theorem in high dimensions. Right. What next? Well, again, so there's up to a constant in the exponent, so one would like to know what the constant is. However, someone in this room has thrown a spanner in the works. So Paul Ballister here has shown that even with these so-called easy supercritical models, you can't actually compute the exponents in general. Which is quite astonishing, actually. That even dimension 2 and greater, so these are the easy ones, remember. These are the ones where some finite set just goes, and you just want to know what the threshold is. We know it's polynomial, we'd like to know what the exponent is. And actually, it turns out that in general, we can't compute that. And you could say, well, okay, that's supercritical, what about critical, which perhaps the ones we really care about. The problem is that all approaches that we currently have to proving results about critical models, they induct on R, where R equals 1 is really supercritical. So we start with supercritical. You have to solve the problem supercritical first before you can do 2 critical, like 2 neighbor, and you have to solve that before you can do like 3 neighbor. And all of that's entirely because of what I said here about when you've got some object that's growing, on the face, it looks like a process that's got 1 less R, see what I mean? So that's a problem, and there are other problems about, but these are, yeah, there's a more minor thing, this is a major problem. So if not that, then what? Yes?
What's uncomputable mean?
Paul is probably better placed to explain this than I. But so you can encode. So
Not a computable real number. Is that what I mean?
So you can encode as a supercritical model any program you like. Yeah, and and you can show that if the program holds, then if the initial density is smaller than some threshold, it doesn't percolate. if it's greater than that threshold, it does percolate. And if it doesn't halt, the same thing is true with a smaller threshold. So if you knew the critical probability, you'd know if it halts or not. And that's true for an arbitrary program. I think that's about right. Yeah. So it seems that the major applications are in other areas of probability and statistical mechanics. And these seem to possibly be the two where there's most chance of where there's most interest. So Christina's already talked a bit about these today, but on Wednesday, Fabio's going to talk more specifically about the potential applications of this general model to kinetically constrained spin models. So I'm not going to mention that at all. I'm just very briefly mentioning Glauber dynamics. So every cycle lattice is plus minus, and they have two clocks. They have plus clock and minus clock. And if clock rings, then it looks to see if one of the configurations X around that site is completely plus, say. If it is, it becomes plus. So when the object family is just the D nearest neighbor model, this is the usual zero temperature Glauber dynamics with Ising model. Okay. This is a very well-known folklore conjecture that what density do you need to almost surely fixate at plus? We seem to be a long way from proving this still. The state of the art, Rob Morris proved that this tends to a half as d tends to infinity. So this is likely to be very different. So this is because Rob has just written a beautiful survey article of modern bootstrap percolation, but much more an emphasis on open problems and conjectures in these areas and others. It's not on the archive, but Rob is very happy to send it to anyone who's interested. Okay, and finally then, so if this previous problem is likely to be very hard, then what can we do instead? So the conjecture is if it's critical, then the critical probability is less than 1. And that may well follow from combinations of techniques of these people and our results in bootstrap percolation. Yeah, so I'll leave it there. I think I've run out of time, so thank you very much.
Questions for Paul?
So, even though these things are non-computable, you could still imagine a result that says, in this family of models, the threshold is order of 1
Yes.
log n to a constant.
Yes. Yeah. So we initially thought that solving the supercritical problem would be an easy thing to do, and just a question of time before someone did it. But then it turned out we couldn't even do a sort of interesting general class like that. I mean, yeah, some very basic things you can just solve, of course, but more general, any kind of general class, we don't really have any idea.
That wasn't the question.
Was it not a question?
You might still know that for every supercritical one, it is a polynomial, even though...
We know it's polynomial, yes.
Okay. So
We do know that.
You might imagine in 3 dimensions you could show that for every model in this class, the threshold is 1 over log n to some power, even though you can't say what the power is in a nice way.
I think that's what we can prove. I think that was what the result was, yeah. So for supercritical, we do know... maybe I didn't mention supercritical. In high dimension supercritical, we do know it's polynomial. We just don't know, we don't know how it is, yeah.
Any questions?
Do you also know it for subcritical, so in high dimension?
Yeah, so unlike a lot of percolation, it seems that the methods for the two-dimensional results should just extend to high dimensions with not very many changes, although I'd say that very tentatively. No one's written anything down, but it seems like that it probably would just go through, yeah. We haven't actually attempted to do that yet.
Have you had to compute the exponents for the subcritical?
The subcritical? You mean the actual critical probabilities?
But wasn't this is the polynomial?
Supercritical.
Oh, the supercritical. Oh, and that's what you can do.
Yeah, so we can't do, yeah. So we can do it in one dimension, which you have to do to get the two-dimensional result. Yeah, greater than that, we can't do it.
One last question before we swap over to our next speaker. Anyone else? Okay, let's thank Paul again.